Hello and welcome back. In the previous videos, we looked at bubble sort. We then optimized bubble sort so that it runs in big O of n time complexity in the best case. In this video, we will be looking at another classic sorting algorithm, which is selection sort. Selection sort is also big O of n square time complexity algorithm. And in this video, we will be looking at it step by step so that we break down the core logic and understand how that works. So the core idea of selection sort could be divided into two simple steps. The first step is that we will be selecting something, right? As the name selection sort suggests, we will be selecting the smallest element from the unsorted part of the array and we will place it at the beginning of the unsorted part. Let me give you an example. Let us consider the following array. Imagine you have 5, 1, 4, and 2 as your array. Now this is clearly unsorted. So the idea here is to find the smallest element and place it at the beginning. So let us say that initially the smallest element is 5, which is the first element. We now check if 1 is smaller than 5. Yes, it is. So we will update the smallest to be 1. We then say, is 4 smaller than my smallest? No, that is not. So the smallest still remains 1. We now ask if 2 is smaller than 1. No, it isn't. So we found out that 1 is the smallest element and we will now swap it out with the element at the beginning of the unsorted part. So this array now becomes 1, 5, 4 and 2. So 1 is now a part of the sorted array and the remaining 3 elements are unsorted. So if you continue step 1 n minus 1 times, you will end up with an array that is completely sorted. So this is the basic idea of selection sort, where we repeatedly select the smallest element from the unsorted array and we will place it at the beginning of the unsorted array. So I hope this is clear. Now let us jump into a visualization so that we can visually see what happens. So this is our input array. The input array consists of 5 elements and it is unsorted. We will be tracking the number of steps that we will be taking in order to sort this. So initially we will assume that the entire array is unsorted and the first element would be assumed to be the smallest element. Now we scan through the entire array and we see if we can find a smaller element than 5. So we say 1 is smaller than 5, yes it is. And we mark 1 in blue color to signify that this is the smallest element that we could find so far. Now we'll compare 4 with the smallest element so far. 4 is not smaller than 1. We'll check if 2 is smaller than 1. No, it isn't. And finally, we will compare 1 and 8. And 1 still happens to be the smallest element. And now we have found out that 1 is the smallest element. So we have essentially selected the smallest element from the unsorted part. And we will now swap it with the element at the beginning of the unsorted part. So 1 is now sorted and this part of the array is sorted, the rest of the 4 elements are unsorted. So these 4 elements now form the unsorted part of the array and we will assume that 5 is again the smallest element. We will now say 4 is smaller than 5, yes it is. So temporarily 4 is now the smallest element so far. We will check if 2 is smaller than 4, yes it is. So 2 has become the smallest element so far. And 8 is not smaller than 2, so 2 remains the smallest element out of all the 4 elements and we will swap 2 with 5 so that 2 goes to the beginning of the unsorted part. So again let us assume that 4 is the smallest this time and we will compare it with the rest of the elements. So is 5 smaller than 4? No it isn't. Is 8 smaller than 4? No it isn't. So we have found out that the smallest element is already at the location where it has to be, that is at the beginning of the unsorted part. So we will swap it with itself and that will lead us to this array where 3 elements are sorted and we are just left with 2 unsorted elements. So now again we will assume that 5 is the smallest so far and we will check with the rest of the elements. There is only one more element, so only one comparison will be enough. Since 8 is not smaller than 5, 5 is the smallest so far and we will swap 5 with itself. So with that, we now see that the entire array is sorted and we only required 4 iterations. So earlier we had seen that we had to repeat step 1 n minus 1 number of times. So n here is 5, so we repeated step 1 4 times and we see that the array is sorted. So one might ask, why is 8 not marked in green? So this is to show that we only require n minus 1 passes and if n minus 1 elements are sorted, the last element automatically ends up at its right location. So as I've said earlier, we only require n minus 1 passes, and this signifies that n minus 1 passes are enough to sort an array of n elements. So we understood the logic and we also looked at the visualization, so that solidifies our understanding, right? So now let's go ahead and write the code. So as you can see, this is a simple program. All we have is we will display the array that will show the unsorted array, right? And we will apply selection sort, and then we will finally display the sorted array. So we need to write the selection sort function that will read an array through reference, and we will sort that array. All right, so the first step is to do step 1 n minus 1 times, right? So let's write a for loop for that. So for every integer I that goes from 0 and array dot size minus 1. So this loop does something n minus 1 times. And inside this, we will be writing step 1 so that step 1 gets executed n minus 1 times. So every step begins by assuming that the first element of the unsorted array is the smallest, right? So let's now assume that our minimum index or the index of the element which is the minimum is the first element. Now we will scan through the rest of the array. So integer j will go from I plus 1. So all the elements after I and j has to be less than array dot size and j plus plus. So this loop basically means that we are going through all the elements in the rest of the unsorted part and we will try to find the smallest element. So if I find out that any array of j is smaller than array of minimum index, I can now update my minimum index to be j. So we are saying that if I find an element which is smaller than whatever I assume to be the smallest, we will update the smallest, right? So after I go through the array, I will have the index of the smallest element and I need to place that at the beginning of the unsorted part. So I can simply swap it out so that array of minimum index is at array of I, right? So initially when I is 0, we will find some minimum element and put it at I0, which is the beginning. And then in the second iteration, we will take the second smallest element and put it at array of 1. So 1 is the second smallest element, right? So in that way, we will be completing the entire sorting. And by the end of it, we should be having the sorted array. I will also add some comments here so that it becomes easier to understand. Now let's try to run this file to see if we can sort this unsorted array. So as you can see, the first line is the unsorted array and the second line is the sorted array, which is clearly sorted. So that was all about selection sort. It is a very simple algorithm. You just have to remember these two steps individually so that you can write down the code yourself. Let's now understand the time complexity of selection sort. We will look at time complexity from the number of steps perspective, where we look at the total number of steps that the algorithm does, and we will assume that each step takes a constant amount of time, and we will multiply the constant with the total number of steps, and that should give us the time complexity. All right, so let's take a look at these two loops. So I goes from 0, I becomes 1, and it goes all the way until I equals n minus 2. Right, I is less than n minus 1, so I has to become n minus 2, and after that it will not execute. So the corresponding values of j will be j equals 1 and it goes all the way until n minus 1, right? Because j is 1 greater than I, and if I is 1, j begins from 2 and it goes till n minus 1. Similarly, when I is n minus 2, j becomes n minus 1 and it goes till n minus 1. So the total number of comparisons that we do in this particular step will depend on the number of different values of j. In the first case, as you can see, j goes from 1 to n minus 1. When I becomes equal to 1, j goes from 2 to n minus 1, so that is n minus 2 number of steps. Similarly, at the end, j goes from n minus 1 to n minus 1. So basically, j only executes once and that is for n minus 1. So we only have one step. So if I sum the total number of steps, that will be n minus 1 plus n minus 2, so on until we have only one step towards the end. So this summation of the total number of steps will form an arithmetic series whose sum will be n minus 1 over 2. Alright. So n into n minus 1 over 2 will be the total number of steps that selection sort performs. So this algorithm will approximately be a quadratic expression. So from a time complexity perspective, I can say that the time complexity of selection sort is big O of n square. So in terms of time complexity, selection sort is not great. It is a quadratic time algorithm. Let's now look at space complexity. So if you take a look at the code, we are not using any additional data structures, right? We have no additional data structures or arrays. We only use a constant amount of memory, which is for this and for to keep track of the loops. So this makes selection sort a big O of one time complexity algorithm, right? In terms of space complexity, selection sort is big O of 1. So in the introduction video, we had seen that any algorithm that uses a constant amount of extra space, that is called an in-place sorting algorithm. So that makes selection sort an in-place sorting algorithm. Now let's take a look at some of the key features of selection sort. So the first thing to notice here is selection sort is not a stable sorting algorithm. So if you have two elements which have the same value, their relative order might not be the same after sorting, right? So let me give you an example. Imagine you have an array of 4, 5, 4 and 3. In order to differentiate between the two 4s, let me write one as 4a and the other one as 4b. Now let's do one step of selection sort. Let's take the smallest element and swap it out with the element at the beginning of the array. So here 3 is the smallest element, right? So we will pick 3 and swap it out with 4a. So from this you can clearly understand that in the input array, a had appeared before b, but after running one step of selection sort, we can see that 4b now appears before 4a. So the relative order of equal elements is not maintained, and because of that, selection sort is not a stable sorting algorithm. The next thing to notice is that selection sort is an in-place sorting algorithm. We had seen that it only uses a constant amount of extra space, and because of that, it is an in-place sorting algorithm. The final point to note here is that selection sort is a comparison-based sorting algorithm. Since we use simple comparison and we do not use special techniques like hashing or counting, that makes selection sort a comparison-based sorting algorithm. So that's it for this video. We looked at selection sort in a holistic manner and we understood the core logic. In the next video, we will be discussing about insertion sort, and later we'll also look at merge sort and quick sort. If you found the video to be useful, please like the video and subscribe so that you don't miss our future uploads. Thank you.